Hello, computer science friends. This is Mr. Creighton, and we are going through lesson 2 using binary and the ASCII table. Essential question: how are the binary bytes linked to the ASCII table, and what are parity bits? So a lot of stuff here. Well, first of all, binary bytes, that's a new term. ASCII table, that's something new. And parity bits, holy cow, we got all sorts of things going on today here. So let's get right to it. First of all, let's talk about the ASCII table. Now, the ASCII table is a standard code that is utilized to deal with keyboard characters that you type and then go into the computer as their binary equivalent. So, some key things here. This was created in 1963. It uses 7-digit binaries to deal with the 128 different characters to encode into binary. Now we are going to take just a snippet of that table. As you can see here, I've got the letters A through Z and the space here because we're going to do some encoding and decoding. So again, we can see here these are binary zeros and ones. So kind of continuing here, let's get some of the other information dealt with here, especially the vocab here. We're going to start with byte. It's again the basic unit of information for storage and processing. A byte consists of 8 adjacent binary digits. Those are known as bits from over here. And we'll get ones and zeros. Now, if we go ahead, take a look at the bit. That's just short for binary digit. It's the smallest unit of data in a computer. So these items here, these pieces here, these are 7-bit values. So let's start using bits instead of digits here. Kind of continuing here. Again, a bit has a single binary value, either 1 or 0. Makes sense. Now, very interestingly here, we have a bit and a byte. And if we have a nibble, that's 4 binary digits, or half of a 8-bit byte. Holy cow. Now, when we have such things, it's kind of tongue-in-cheek here a little bit, where a half a byte is a nibble, and that kind of makes sense in terms of eating things here. One of the key things here is that a nibble is used to represent a single hexadecimal digit, and you're saying, what the heck is a hexadecimal? We're going to talk about that in lesson 3. So moving on to the ASCII table binary combination here. So again, I have repeated the table there, just copied and pasted it here. Now, one of the things here is we are needing to translate or decode the binary to get the capital letter that goes with it. So all sorts of ways to do this. What I do is I look at the right side here, and I have a 1, 1 followed by, and then left of it is 4 zeros. So I'm going to go ahead and look down the first column. I see this one here, but that doesn't kind of fit the entire thing, so that goes away. This next one, I don't have any, and oh, here we go. I found it. We got C. Okay. Now continuing here, oh man, I got 4 1s on the right side here. I'm looking at these guys. That should be pretty easy to find, kinda. Except the issue here is that these bits are broken up a little differently, but they're all the same value. So that means this one here is O. Okay, capital O, of course. As we kind of continue here, now I'm looking for two zeros and a 1 here, so I'm looking for this guy here. Nothing. Oh, this one is kind of close here, but doesn't really fit the left of that here. And oh, here we go. Found it right here. So that's going to be capital D. Kind of continuing here. I've got a 1, 2, 0. Oh, I got a 1, 0, 0, 1, 0, 0. So I'm going to kind of go a little hunting here. Oh, here we go. Found it. That's capital I. Moving on here. We're back to, okay, I got a 0 with 3 1s. A 0 with 3 1s. Oh, here we go. Looks a little different there, but again, the spacing is just there in the eye of the user there. And then finally here, we're going to go back to 3 1s in a row. Oh, found it right away here. So 3 1s in a row. That's going to be G here. So again, it makes sense that if I had a secret word, it would have to do something with programming here. So again, just being able to use these to translate from binary to English and vice versa. Speaking of that, this practice here, we'll do this maybe in a day or so here as kind of a follow-up. And again, this will be a chance for you to encode a short message, and then we'll swap with somebody in the class and see if they can decode it. So that takes care of the first part of our essential question. Binary bytes linked to ASCII tables. Now next we're going to take a look at the parity bit scenario here. Now parity bits are used to make sure that when data is transferred, that the transfer went without a hitch and that the data that you received was the data that was sent to you. It's a way to kind of check to make sure the data is correct. I know in mathematics many times teachers want you to check your answer after you've done all the work. Some students do, some don't. But it's a safeguard to make sure that the final version is correct. So again, a parity bit is normally put on one end or the other, in this case the right end. And again, there's a system here based on the type of parity that's going on that it can use that to see if the data is correct or if there's an error there. Okay. So if we look at the other part of this, this is just the plain old A from the table. Okay. So we're going to use this in the next couple of kind of topics here as far as this lesson. So let's take a look here. They're asking us here, again, this is the same table that we started with today, but it's got a parity bit which is bold-faced. So I'm just going to put a little yellow dot on these parity bits. Now, it's not haphazard. It's not just random what number goes there. So we're going to try to figure out by answering these 3 reflection questions here. So first of all, how many 0 bits are used to represent the letter C without the parity bit? So we're looking right here, but we're not going to use the parity bit. So how many zeros? I got 1, 2, 3, 4. How many 1 bits? 1, 2, 3. Okay, and there's my 7 that we have talked about earlier to represent the ASCII character C, capital C. Okay, what was the parity bit that was used? Well, the parity bit is this guy right there. So we used 1 for the parity bit. So if we take a look at that, the next one, parity bit right here, for D is 0. And again, the next one there for E is back to 1. And then here for F, it's back to 1. So there is a process here. So the next question here, why is 1 the parity bit for J rather than 0? Well, let's go ahead and take a look at J. J is 1, 0, 0, 1, 1, or 0, 1, 0, and then my parity bit. Well, if I go ahead here and count the ones, I have 3 of them. The parity bit needs to be a 1, so then now I have 4 of them. So I had 3, now I have 4 parity bits. We like 4. 4 is even. The parity bit will cause the entire number of ones in the 7 bits plus the parity bits needs to be even. So we are using even parity here. So we should say here, why is 1 used? To make the number of 1 bits an even number. Okay, so that's the key, and we are doing even parity. So as we can see here next, we're talking about even parity. So in the case of even parity, for a set of bits, the occurrences of bits whose value is 1 is counted. If that count is odd, then we set the parity bit to 1, which makes it then an even. Okay, if the count of ones is already even, then we set the parity bit to 0. That keeps it even. So this is even parity. Now, out there at times, there's odd parity as well. Okay, so again, we are going to focus mostly on even parity. With this type of thinking, we have another statement here. Check digits. That idea is related to parity digits, and we will have a couple problems on the worksheet dealing with check digits. So with that, takes us to the end. Hopefully this helps you get through your notes and helps you get a great start on the Lesson 3 worksheet. Actually, this is Lesson 2. Sorry, it's Lesson 2. I was looking at the title there. So, well, adios. This completes Lesson 3, and stay well, my programming friends.